Welcome to the lecture series on chemistry of environment. We are discussing about fundamental aspects of chemistry relevant to environmental studies. In the previous class, we discussed about thermodynamics aspects, and today we are going to see about chemical kinetics aspects relevant to environmental studies. Really, the chemical kinetics is about the study of rate of a particular chemical reaction, and the mechanism by which it proceeds is about chemical kinetics. Okay. And commonly, the chemical kinetics measure how fast the products are formed and how the reactants are consumed is governed by the rate values. Especially this is very important in the aspects of wastewater treatment, how the pollutants, how fast they are eliminated from the waste stream or degraded in the waste stream. Let us consider a general chemical reaction. Two reactants, namely A and B, react to form the products C and D. This may be the reactants may be organic based or something else, and usually on oxidation they will be converted to carbon dioxide and water. So, like this it can be any other reaction, and we will really see as the reaction proceeds, the concentration of the reactant A and B will decrease in the system with respect to time, whereas at the same time the concentration of the products C and D will increase with the time simultaneously. So, the rate of the reaction is very important, and it is defined as a change in the concentration of any of reactant or products formed in the reaction per unit time. This is what the rate of a particular reaction, and we should know how fast the reaction proceeds in a particular reaction. And usually the rate can be described with respect to change in concentration of the two reactants on products. In the general equation we have seen two reactants A and B. So, here the change in concentration is decreasing. So, minus sign with respect to A as well as B with time, whereas if we consider the products, it is plus sign, you can see here, and the C and plus here it is formed increasing. So, for a general balanced reaction return, the stoichiometric like x y in the reaction also well takes place, and the products L and M. So, the reaction rate is given by decreasing minus 1 by x. This is what in the stoichiometric equation, and similarly with y, this is a 1, whereas in the products formed it is L, and here it is increasing the change in concentration of C as well as another product may be D. So, this is also will increase how fast the products are formed or how fast the reactants are consumed in a particular chemical reaction. So, similarly here also waste, how fast they are eliminated, that is important. Generally there are factors influencing the reaction rate of a particular chemical reaction. Generally these are the parameters or influence the rate of the reaction, that is nature of the reactants as well as products formed, and concentration of the reacting species. What are the initial concentration of the reacting species, temperature of the system, presence of catalyst, surface area of the reactants, as well as exposure to radiations like UV or something. Okay. So, these are the various factors which can influence the rate of the reaction. For example, in a particular reaction, both the nature of the reactants and products are very important. Okay. If the reactants are similar and products also two reactants are similar, then the reaction will proceed faster. If they are different nature, the two reactants, and the rate may be slow also. For example, inorganic reactants, if it react, they will proceed faster. If it is a reaction between inorganic and organic, then the reaction may be somewhat slow. For example, you take the oxidation of iron with the potassium permanganate, ferrous with the potassium permanganate, both are inorganic, it will react faster, whereas potassium permanganate with oxalic acid being organic, it is somewhat slow, and usually it is initiated by warming the reaction in the titration itself. So, similarly, the concentration of the reactant species is high, it will faster. Temperature of the system is also high, definitely it will speed up, especially for chemical reaction. This is also true for biological reaction up to certain temperature. And presence of catalyst also will speed up. Surface area of the reactants involved, suppose solid particle, and exposure to radiation also will speed up the rate of the reaction. And we can write rate equations, rate law also for a particular chemical reaction. For example, let us say A and B reacts with the X mole and Y mole to form the product C and D with the L and M moles. Okay. So, the rate of the reaction can be given as rate is proportional to concentration of reactant A and concentration of reactant B. That proportionality can be removed by introducing a constant k, small k. Usually it is represented in chemical kinetics small k, and this is a proportionality constant, and it is also known as very popularly the rate constant, and sometimes also it is referred as velocity constant of the reaction. So, this small k is very important in describing the rate of the reaction, which is normally known as rate constant. Okay. So, in the above reactions, X and Y represents the order of a particular reaction with respect to the reactants A and B. So, the value of k, rate constant, order of the reaction with respect to A are experimentally determined for a particular given reaction. Okay. And we cannot derive anything based on the stoichiometric equations. So, the rate constant in the above general equation k represents the rate constant, or sometimes it is also known as specific reaction rate constant, and usually it is defined as a rate of the reaction when the concentration of each of the reactants is unity in a particular reaction. Okay. So, in a rate constant, the rate is defined as the rate of the reactants when the concentration of each of the reactants is unity in a particular chemical reaction. So, when concentration of A and B in the general equations is unity, then the rate constant is equal to the rate of the reaction. So, under this condition, if it is a unity, then rate constant and rate of the reactions will be the same, and the temperature of the reaction also can change the rate of the reaction, and the value depends on therefore the temperature of the reaction mixture. And in chemical kinetics, there are two terms important. One is especially the order of the reaction is very, very important, and the other one is based on the stoichiometric equation, the molecularity. The order of a reaction is defined as a sum of the exponential power to which each concentration is raised in the rate expression, and this is normally known as order of the reaction, and this is an experimental quantity. Based on particular chemical kinetics reaction, we have to find out experimentally what is the order of the reaction, whereas molecularity of a particular reaction is defined as a number of atoms or molecules taking part in an elementary step leading to a particular chemical reaction. So, this is based on the stoichiometry of the reaction, we can get the molecularity of the reaction, whereas order we have to find out by conducting experimental studies. We have to find what is the order. Usually the rate determining step of the equation, what is the number of moles of the particular reactant involved is order, and usually order and molecularity may be different or may be equal also sometimes. And some of the characteristics of the order of a reaction are: the magnitude of an order of a reaction may be 0 or fractional values sometimes, and usually integral values. Okay. So, it can be anything, maybe in the order of the reaction, sometimes also negative, 0, fractional as well as integral values, whole number. And for an elementary reaction, its order is never fractional since it is one step process. So, usually the order will be whole number, and order of a reaction should be determined only by experiment, and it cannot be predicted in terms of stoichiometry of the reactants and products taking place in this particular chemical reaction. And simple reaction possess low values of the order like n is equivalent to 0, 1, 2 like this for a general reaction, and reactions with the order greater than 1 or equal are usually called complex reactions. Okay. And such type of complex reactions or higher reactions are usually very rare. And some chemical reactions also show fractional order depending on the rate of the particular reaction. And higher order reactions may be experimentally converted, sometimes for convenience of a design we can convert it into a simple order reaction, normally known as pseudo order reaction, by using excess concentration of one or more reactants. Suppose if it is a bi order reaction, order is 2, we can take one reaction and convert it into a unimolecular reaction, or I am sorry, first order reaction by taking one reactant's concentration high. Let us simply derive what is the first order reaction rate equation or the rate constant for a first order reaction. And in the first order, the rate determines depends on the concentration of only one reactant. Okay. So, the first order reaction is in which the overall rate of the reaction is proportional to the first power concentration of on one of the reactants only, and hence these type of reactions are called first order reactions. Okay. Let us say reactant A alone takes place in a particular reaction, it is getting converted into products, and the rate of the reaction, as we seen before, that is equivalent to minus change in concentration of the reactant with respect to change in time. From 0 time, 5 minutes, what is the concentration remaining, 10 minutes or 1 hour, what are the concentration remaining, we have to find out, and that also can be put with the K 1 first order rate constant, that depends on what are the concentration of the reagent reactant to the rise to the power of 1. So, such type of reactions are called first order reaction. So, here the K 1 is a rate constant for the first order kinetics, and usually any chemical reaction at the starting time 0, the concentration will be the, let us say, A. Normally the concentration will express in moles per liter or moles per decicube. After the reaction has proceeded for some time, let us say t times, 5 minutes, maybe 10 minutes, like this, the concentration of the A then that has reacted, let us say x mole of A is reacted. So, the concentration of the unreacted A remaining at time will be T will be A, that is the original concentration, minus x moles per liter. So, the rate of the reaction will be dx by dt. So, change in concentration. So, first order reaction, if you put it, rate is equivalent to dx by dt, that is equivalent to K 1 into A minus x. This is a derived from the rate equation as before. And if we suppose we integrate this equation within the limit say times 0 and x concentration, initial concentration is 0, and this is a integration. If you do this and bring the time one side and the reactant concentration one side, and this equation will be reduced to change to minus ln A minus x, that is equivalent to K 1 into t time plus c, that is normally the c is normally known as integration constant. So, when you look at the time beginning of the reaction, time is 0, the concentration of x, that is a product formed, is also 0. So, in the equation, if you put it the value c, this value, it will be coming to this form. By putting the value of c, this equation will take this form, and rearranging this, that is, you bring the rate constant on one side, the time and reactant concentration the other side, this equation will go like this ln. This can be converted into log by multiplying by 2.303. So, K 1, that is a first order rate constant, is equivalent to 2.303 by t time log A, that is the initial concentration, and A minus x, that is a concentration of the reactants remaining at time t. Okay. So, this equation is called first order equation, and usually in the rate constant for first order reaction is time power minus 1, normally SI unit, it is second power minus 1. So, this equation is called first order rate constant equation. And some of the example that follow first order reaction is well established in the literature. For example, especially in the wastewater treatment, the biodegradation of organic matter, we follow BOD, biological oxygen demand. The rate depends on the organic matter actually present in the water, normally measured with a BOD. And similarly, disinfection for killing the microorganism also depends on what is the microorganism concentration. Okay. So, these are all first order. In the biological reaction, it depends on the organic matter, there is a BOD, whereas in the disinfection killing the microorganism, it depends on what is the microorganism concentration with respect to order this. And similarly, all nuclear reactions are first order kinetics. Okay. Uranium disintegration, uranium 238 converting into thorium by emitting alpha rays. Okay. So, all these reactions are well known reactions for first order reaction, and if you plot it, that is time in x axis and log A at time, what is the time remaining from with reference to initial reaction time 0, and if you plot with various time, you will get a straight line. And this is a pattern by putting log A at a different time and concentration with respect to time. If you are getting a linear one, these any type of reaction, it follows first order kinetics. And it is also important to know what is the half life period, T off, generally referred as T off, whether it is biological reaction, nuclear reaction or any other chemical reaction. We have to find out, especially for the first order or other orders, the half life, that is the time taken to reduce 50% of the concentration. This is also very important in kinetics. That is, the half life is defined as a time required to reduce the concentration of reactant to 1/2 of its initial value. Okay. And the T half values can be calculated based on the first order reaction kinetics. So, we know this is a first order reaction. Okay. And suppose the amount reacted at the T half time is 50%, that is x is equivalent to A, that is the initial concentration divided by 2, that is the x concentration remaining at T half. So, using this in this equation, the first order equation, it will take this form, and then if you rearrange this, it will go to this form and log 2 put the values, and finally, this equation will be reduced to T half is equivalent to 0.693 divided by K 1 rate constant in second. This is a half time required for any reactions follows first order using this. You can see here the T half is independent of initial concentration, and it is also inversely proportional to the rate constant of the reaction. The T half is inversely proportional to the rate constant. Okay. So, this reaction is also very useful in determining the time required for completing the particular reaction. So, this first order reaction and the T half are very important and determining how long the experiment or the treatment has to be given in eliminating a particular thing. As I mentioned before, suppose a particular reaction is a order is 2, and it is also convenient to make the rate depends on only one reactant. So, that the design of the reactors, everything will be very simpler. So, always if it is a second order reaction, usually a scientist and chemical engineer will be interested in reducing it to pseudo order. Okay. So, pseudo order means really it is a second order. By taking one concentration of the reactant with respect to the next one, at least 10 to 100 times more, so that the reaction rate depends on only one reactant, the lower concentration. These type of reactions are known as pseudo first order reaction. For example, ester hydrolysis can be carried out in acid medium and alkaline medium. If it is taken an alkaline medium, ester will be hydrolyzed to respective acids and alcohol. Okay. it is a second order reaction. Whereas, the same reaction if it is carried out in acid medium by taking excess amount of large amount of acid, so that the reaction ester hydrolysis in acid medium will follow a pseudo first order kinetics. These are the well established pseudo first order reactions. Also, it is possible some reactions may follow zero order kinetics. Okay. Here in the zero order kinetics, rate is independent of the concentration of the reactants. Okay. For example, A gives product, the rate is independent of the initial concentration of the reactant A. So, such type of reactions are known as zero order reactions, that is initial concentration at the time of the concentration amount of reacted is equivalent to, the difference is equivalent to zero order kinetic constant into time. Okay. So, this is A 0 is the initial concentration and A t is the concentration of A at time t, and here the half life is equivalent to A naught divided by 2 k, and usually the rate constant in this one is moles per liter for seconds. So, zero order kinetics, it is moles per liter per second. Okay. Some of the examples which follow zero order kinetics are enzyme catalyst reaction are zero order with respect to substrate concentration, and also decomposition of gases on the surface of metallic catalysts like hydrogen iodide on gold particle follows zero order kinetics, and some of the photochemical reactions also follow zero order kinetics, and which if you plot time versus concentration, you will get a straight line. Okay. This indicates, such type of plot indicates it a particular reaction follows zero order kinetics, and the unit for rate constant also differs with the order of the reaction. For example, for first order, the rate divided by concentration of initial reactant concentration is the rate constant. Okay. Here, if you put the rate, that is moles per liter per second, this is a rate constant divided by moles per liter, actually the rate constant comes to second power minus 1, time power minus 1. So, rate unit, this is a 1, and whereas the concentration of the A, if you put this, both will be getting cancelled. So, the rate constant unit for first order is second power minus 1 or time power minus 1, and same thing if you do like this, the second order rate divided by A square or A into B. So, moles per liter square. So, in this the second order rate constant unit will be mole power minus 1 to liter per second. This is for second order, and for nth order, second order, third order, like this we can write like this in this form. This is a general equation. So, for first order kinetics, it is time power minus 1, that is a rate constant unit. And as I mentioned before, rate depends on temperature. If the temperature changes, the rate constant value also changes. And one of the scientists popularly investigated this phenomena, how the rate constant and temperature varies by Arrhenius. He postulated a equation, general equation, what is known as Arrhenius equation, and this is what the equation. The rate constant is equivalent to A e power minus A divided by R t. So, here the K is rate constant, E A in this equation is the activation energy, and A is a frequency factor, and R is a gas constant, universal gas constant, T is a temperature normally expressed in Kelvin. So, this is the Arrhenius equation, and if any experiments carried out to different temperature, this equation will take this form, that is the rate constant at T 1 and T 2 will be different, and this is a Arrhenius equation, in which we can find out what is the activation energy for a particular reaction by carrying out measuring the rate constant at two different temperature, and we can find out what is the activation energy for this reaction, and this also can be plotted ln k versus 1 minus t, and from this we can find the slope value of the straight line plot will give you the activation energy. Okay. From this, the slope of this plot we can find what are the activation energy. So, by varying the temperature experimentally we can determine, and this is called Arrhenius equation, who investigated how the rate constant varies with temperature. So, to sum up, any chemical reaction, as I told you in the previous class, thermodynamics and chemical kinetics are very, very important. Chemical kinetics, in which the deals with the rate and ultimately the rate constant for the particular reaction, is very, very important. We should know what is the order of the reaction, and based on the order, whether it is a first order, 0 order or second order, we can find the rate constant, which will help in determining the half life period for a particular reaction, and ultimately the time required for carrying out or completing the reaction. This is very, very important, because suppose in environmental studies we are interested in eliminating how fast the pollutants are eliminated from the system, or what is the time required really to carry out the reaction. And biological reaction, we do other advanced oxidation process, chemical processes, everything is used for eliminating especially the recalcitrant non-biodegradable processes. Generally biochemical reactions are little slow, whereas chemical reactions are fast. So, the time required to complete a particular reaction to reach the permissible limit of the standard value for a particular pollutant is very, very important. In this aspect, the chemical kinetics will throw more light, and that is very important. So, even complicated reactions can be converted into pseudo first order reaction, so that the reaction design everything will, we can make it simpler design. So, there are ways to convert it. In these aspects, along with thermodynamics and chemical kinetics are very, very important in studying this or eliminating the pollutants from waste stream. Thank you.